To start this demonstration, we open Apex and pull on File, Open. We select the project.apex file and click Open. Here we see the pre-built subassemblies with which we will demonstrate stress variation on a prismatic beam due to a bending load. For this demo, we have built two different beam sections with different cross-sectional shapes but the same area and length. There's a rectangular beam and an I-beam. Both have a cross-sectional area of 0.0008 meters squared. We will run the models to compare the results of stress due to the same bending moment applied to both beams. As with the previous beam demonstrations, each subassembly consists of the beam, a part used as a tool to apply the load, and a block on which the constraints are applied. These three parts are glued together. For the bending case, we apply two 1 Newton forces in opposite directions on our tool to apply bending to the bars. With the length of the moment arm at 0.10909 meters, this translates to a bending moment of 0.218 Newton meters acting on both bars. The model is ready to be run, so let's run it. Right-click on Assembly on the model tree and select Set Analysis Context. When Apex reports that there are no offenses identified and that the current analysis context is ready for the submission to the solver, you can proceed to run the analysis by clicking on the yellow running man. Now that the analysis has completed, let's take a look at the results. Click on the Post tab, double-click on Scenario Assembly. Be sure to have your FEM entity type display set to 3D. In the Models subsection, we hover over the visibility icon on Assembly Rep, and select the empty box to hide all the parts in the subassembly. Next, we hover over the Rec beam and click on the check. We press both buttons on the mouse to fit the model to the screen. The deformed plot of the part will now display. To show the fringe plot of the stresses, we click on the fringe icon. If we hover over the area of the spectrum, we will see that we are viewing von Mises stress. Let's change this to X component. Here we see the top of the beam is in compression and the bottom is in tension. We also see that the variation from negative to positive 41 kilopascals is as we saw in the closed form solution and its graph. Now hover over the visibility icon on the Rec beam and select the empty box to hide it. Then hover over the I-beam and click on the check. We press both buttons on the mouse to fit the model to the screen. As with the rectangular beam, we see the deformed plot and the fringe plot. Since it is still showing the X component of stress, we see that the stress range goes from a positive value of 30 kilopascals to a negative value 30 kilopascals, thus showing that the top of the beam is in compression as equally as the bottom is in tension. This too verifies our closed form solution and our graph. We can use the color spectrum to determine what the stress is at intermediate locations across the beam. Here we see that at the centroid, the stress is 0.